Hi there, guys. Well, we've just done 4n. We're about to do 4o, and this is all about points of inflection. And it's also about sketching graphs as well and using now our first and second derivatives in order to come up with sketches for graphs. There's an important little box here about what the conditions are for getting a point of inflection and also what having a point of inflection implies. So we definitely need to go through this. There's some good definitions there. Then there are three longish questions, which are kind of technical, a lot of algebra through them as well. So we'll have a look at those two. But first of all, let's actually talk about what a point of inflection is. So here we go. This is y is equal to x cubed. And you can see here we have a point of inflection at 0, 0. Okay, and it's where the gradient stops decreasing and starts increasing. Okay, so you can see to the left-hand side of 0, 0 that the gradient is decreasing. We're going from steep positive to less positive, and then after the point 0, 0, we have a little bit positive and then steep positive again. So we've got this concave downwards to concave upwards. Or, of course, you can have that vice versa. Okay, so here we go. There's vice versa. You could say that the gradient throughout here is negative. This is a decreasing function throughout. But you can see that the gradient is increasing on the left-hand side of 0. So it's steep negative to 0. So, you know, it might be going from -10 to 0. So that's increasing. And then it's decreasing again after 0, 0. So we've got concave upwards, and then we've got concave downwards afterwards. Okay. Now, this is all about the second derivative, because that's the rate of change of the gradient. And we'll just look at that in a moment with me writing over this. But other points to notice with these points of inflection is that this one has a horizontal point of inflection. In other words, if I put down y is equal to 0 here, we can see that this is a tangent to the line at 0, 0. Okay, well, you can kind of eyeball that. You can see that. You have to trust me on that for the moment. We're not proving that. But, you know, these don't have to have a gradient of 0 at the point of inflection. For example, if I put in here plus x, now we still have a point of inflection. We still have a decreasing gradient on the left-hand side of 0 and an increasing gradient on the right-hand side of 0 here. But at 0, 0, we don't have a gradient of 0, and that's still a point of inflection. That would still work. Just out of interest, what happens when I put minus there? Or we're getting our normal shape that we're used to for cubics there as well. Okay, now there's still a point of inflection here. There's only one point of inflection. You can see up until this point, we're getting decreasing gradient, so positive to 0 to, well, looks like a gradient of about -1. And then at about a gradient of -1, it's then increasing. It's increasing through 0 and it's increasing on the other side. So same rules basically. We have a decreasing gradient on this side, an increasing gradient on this side. So we have a point of inflection in the center. Okay, so let's have a look at, well, I mean, I was looking at this. Let's just go to this. I mean, what I was basically saying there is from here to here, this is concave downwards on this side, okay? Okay, and you can say that as a description of the curve in your exams. And this, on the other side, you can say this is concave upwards. Okay, and concave downwards is always when we've got the second derivative. So second derivative is going to be decreasing. So it's going to be less than 0. So this tells us about the rate of change of our first derivative. Okay, so we've got a decreasing gradient here. You know, it's strong positive to less strong positive to 0, it turns out in the middle there. And then on the other side, of course, we're getting dy dx is greater than 0. We have an increasing gradient. Okay, now in the center, and for all points of inflection, in fact, we get the second derivative in the center. Happens to be when we've got 0 here, but we can also say when we put in C. That's I think what the book does, but I'm just saying here, at this point here, this x point here, we notice that we have the second derivative is equal to 0. Now, that links to this point here. So let's just pick this up. And there's two really important bits in here. It's this and this. Okay, so this first bit says if f has a point of inflection, so inflection implies, so if, then it implies that we have our second derivative at that point. That second derivative at that point, they're saying for C, I'm just going to say for X here, is equal to 0. But it's not sufficient to say that f dash dash of X implies a point of inflection. It doesn't. Okay, now we had a look at a graph before. I mentioned that x to the power of 4, y equals x to the power of 4, has a second derivative of 0 when we put in the point of 0. So when we look at this point at 0, 0, which we can see is a minimum turning point here. In fact, we can keep zooming in just to check that, but it is. Okay, so this is a minimum turning point, but you'll find out that the second derivative at that point is 0, but it's not a point of inflection. So that's your case where it's not working. By the way, it's just kind of an interesting graph, this one. It's a little bit like, it's a little bit like your x squared graph, except for it's, more sort of steep. It fits neater into the sort of square corners, if you like. It's a bit more squared off at the bottom. And of course, it's steeper after x is equal to 1. So anyway, nice graph. Okay, so f dash dash of x is equal to 0. It doesn't show that we have a point of inflection. But if the concavity changes either side, then so if there's a sign change between f dash dash of x, so this is needed to be equal to 0, and then we need to say that there's a sign change for f of x, f dash dash of x, sign change for f dash dash of x at that particular point. C is x is equal to c, and a sign change for this, or in other words, the concavity changes. That does imply that we have a point of inflection. Okay, so inflection. Okay, so this is true. So if we're asked to prove this, it's not sufficient just to do this. That's really important. Okay, but if we're told we have a point of inflection, then we know this. Now, the question is much more likely to do the second thing. So that's why it's really important to check the sign change of f dash dash of x between the two sides. Okay, let's have a look at the questions then. So we've got question example 29 to kick off with. Okay, so it says consider this function, find all the turning points and determine their nature. So first of all, that's nice and simple. We can just say f dash of x is equal to 0. So we've got 8x cubed minus 8x. We're setting that equal to 0, so we can divide by 0. Sorry, divide by 8, and then we can take out x as a factor. We've seen this one before. And then we've got x and x minus 1 and x plus 1 is equal to 0. And that's obviously implying, that we're getting x is equal to plus or minus 1, which is what we're getting from these two brackets, and a 0 from this one as well. So we can say that that's equal to minus 1, 0, and 1. Okay, now the question also says, and determine their nature. Okay, so we need to figure out whether these are maximum or minimum turning points. Fact is, though, we already know that this is a quartic, and it's a positive quartic because the leading coefficient is positive. So we know that it's going to look like a W, or it's going to have 3 turns as a maximum. Okay, so we also know that positive quartics can look like this. Okay, but when it's got all these when it's got other terms involved, then it's likely to look like the W. Okay, so positive quartics look like this, negative quartics look like this when the leading coefficient is negative, and sometimes quartics look like this, and sometimes quartics can look like, let's try and draw this one out. Hang on, let's try and do, okay, so if we bring this point down, there we go, look, it can look like that as well. So we've got this kind of point of inflection. And again, we've got this 1 turn, 2 turns, 3 turns. Okay, so that's a little bit less obvious perhaps to draw. So you can have a point of inflection and one turning point as well. Now in this case, we can see that we actually have 3 turning points though. So we know that we've got a W shape, something like this. It's not necessarily symmetrical. Okay, so we need to work out their nature. So at this point, let's work out f dash dash of x. That will tell us our nature of these turning points. And so for this, we're getting 24x, just differentiating this, and then minus 8. Now, when we put in minus 1, so at minus 1, when x is equal, let's actually just do this. We've got f dash dash of minus 1. The good thing about functions notation, we can just substitute in there. And I can see, actually, I've made a mistake here. This should be x squared, okay, because I needed to reduce the power by 1. And so then we're getting 24 minus 1 squared, and then minus 8. Now, obviously, that's going to be positive. So that's greater than 0, and greater than 0 implies a minimum turning point. Okay, minimum turning point, talking about having a curve like this, and the gradient is increasing throughout. That's what the second derivative is telling us. Okay, and you can check the other points as well. Actually, I'm not going to do it here, but I clearly know that if I substitute the other two in, I'm going to get a maximum turning point, and then I'm going to get another minimum turning point. I know that from the shape of the graph, but obviously you're going to need to do that for this question here if it was an exam situation, right? Okay, so for part B, find the intervals where the function is decreasing. What we need to know is, so for our part B here, we need to say, well, when is f dash of x less than 0? When is our gradient less than 0? Because if we've got a gradient less than 0, then we know that even if here is less than 0, we know that we've got a decreasing function throughout. Okay, so that comes down to solving this inequality here. And again, we can say we've got 8x cubed minus 8x is less than 0. And again, that comes down to this. That's the same as this. We've already factorized that. So we've got x plus 1, and x minus 1 there. And we're asking, when is that less than 0? So we're now focusing on not the original function, but the differentiated function. Now, if we draw this out, again, we know the shape of this graph, and that's how I would deal with this one. We can see that the shape of this graph is a positive cubic, and then we can look at our solutions. Our important solutions to consider are 1, 0, and 1. This is when we have a sign change for our gradient. Okay, so this is not the original graph. Now, because I can just put in my sketch here like this, I can definitely see that the gradient is positive here, the gradient is negative here, the gradient is positive here, it's above the axis. Again, the gradient is negative here as well. Now, I'm sure the book does this with a table, and does it a little bit neater with the table as well, but you should end up with the same conclusions. Now, you don't necessarily need to be explicit about which points you're putting in to show that sign change. So say, for example, instead of drawing the graph, you are pretending like you put in some points, or you might put in minus 1. I don't think I missed the minus out there. Maybe you put in minus 2. You put in minus 2 into this, and you realize you get a negative answer. Therefore, at this point, up until minus 1, so when x is less than minus 1, we can see that we have a decreasing function. And we have a decreasing function in between here and here as well. Okay, let's just check out how the book does that one. Yep, thought so. It's got a sign table here, and it's talking about what's happening to f dash of x. That's what we care about for increasing or decreasing functions. Now, I think they're going to come up with another sign table later, and they're going to look at the sign change or the sign change for f dash dash of x. And that will then tell us about the concavity of the function at certain points. Okay, so looking for sign changes for f dash of x is telling us whether we have a decreasing function or an increasing function. Looking for sign changes of f dash dash of x tells us, well, do we have a concave upwards or a concave downwards curve? Okay, so this kind of needs to be neatened up here, but your decreasing function, so decreasing is going to be up to here and between here, and an increasing function is going to be between -1 and 0 and greater than 1. Now, obviously, you're going to need to write those as limits. I'm not going to do that here. I'm just kind of running out of space, but you know, you can do that as well. Okay, but this is personally the way I would deal with it. I would sketch out the graph of f dash of x. Okay, so find the intervals where the function is concave upwards, right? Concave upwards is saying, well, when do we have f dash dash of x? Let's think about this one again. We've got, I mean, always draw it out. If you're not sure which way this inequality goes, draw it out. And so we can see this one is an increasing gradient here from left to right. So we're going from steep negative to steep positive through 0 in the center. This is an increasing gradient. So concave upwards means greater than 0. So we need to solve f dash dash of x is greater than 0. So we need to solve this for part C. We're going to say, well, where is f dash dash of x greater than 0? And that's for concave upwards. Okay, concave upwards to start off with. And so where's f dash dash of x? That's this one here. So we're going to say, well, when is 24x squared minus 8 greater than 0? And we can divide throughout by 8, so we're getting 3x squared minus 1 is greater than 0. And then I'll probably just solve that by, well, maybe here you could take the one to the other side, divide throughout by 3. Okay, and we're saying where is x squared greater than or equal to a third? And then we need to think about that one. I draw out the sketch of my x squared graph. Now, the reason why I'm doing this instead of just saying, well, it's factorized, because it doesn't factorize nicely. Okay, so now I'm just considering my x squared graph. Now, x squared is like this, and we're saying, well, where is that greater than a third? Well, it's greater than a third. There's a height of a third there, either side of here. So let's just flip a different color. We're saying it's greater than a third. X is less than this value here, but x is greater than this value here. You've got to be careful with those quadratic inequalities that we are making sure that it splits into 2 in this case. So we've got x is less than the square root of this, so square root of a third, minus the square root of a third, of course. It's got minus the square root 1 over the square root of a third, and we've got x is on the other side. X is greater than 1 over the square root of 3. Now you might know, let's just use a little space in this corner here. You might know that 1 over root 3 can be rationalized to give you root 3 over 3 as well. And you might want to leave your answers as rationalized ones. Let's see what the book does. Okay, no, they've just left it as 1 over the square root of 3. But it's quite normal to rationalize the denominator. And there we go. We can see, what are we getting there? We're getting concave upwards less than 1 over square root of 3 and also greater than 1 over square root of 3. And of course, the other section, so the bit in between, must be concave downwards. Okay, so Interestingly here, it also says set f dash of x equal to 0 to find any possible points of inflection. It doesn't say that necessarily you have points of inflection in between. It doesn't say that you have those points because we haven't checked whether it's concave upwards or concave downwards until we've got to this table. Now that we know that there's a sign change, or there's a change between concave upwards and concave downwards, we know that they're also points of inflection. If it had have said in that table there plus, plus, minus, then you know that in fact you have concave upwards and then concave upwards again. And, that would be like your case of x to the power of 4, where you're just getting one turning point there. So yeah, you do need to check this sign change of f dash dash of x. So now we have points of inflection, and we know the points of inflection are at our roots here, are here and here. In other words, we know we've got a point of inflection here and a point of inflection here. Okay, that is done. Now it says sketch the function indicating any maxima, minima, and points of inflection. Okay, well, should be fairly straightforward now. We know that it's like this. We know that we had turning points. Let's put it on here. We know we had turning points at 0, -1, at 1. We know the graph is like this somehow. We know that at 1 over the square root of 3, get an approximation to that, 1 divided by square root of 3, it's giving us 0.57-ish. Okay, so around about here. That's our -1 over the square root of 3. We've got 1 over the square root of 3 there as well. So we know that those are our points of inflection. We don't know the heights of these things, but we definitely know where we're crossing the y-axis. We're crossing the y-axis at +1. Now, often with quartics like this, you're going to go way off the scale. If I start saying, well, this is +1 here, it might go up to 100. Although it goes between -1 and 1, so I'm suspecting that doesn't happen in this case. Now we should check where our turning points are, and our turning point is definitely at 0, 1. So let me just put that on there for a moment. I might need to get rid of that for the scale. And then we've got to put -1 in here and 1 in there in order to get out the heights at these two places as well. So we need those two. So yeah, actually, we didn't finish that off for part A, by the way. We didn't actually find the other part of the coordinate turning point. We should have. So let's put in 1 here, and we're getting 2 take away 4 plus 1, so that's -1. So there's going to be a point at -1 here. So that's 1, -1. And if we put in -1, we're getting out 2 and -4. Oh, so it's going to be the same again. Okay, so yeah, because these are just even powers on x. So we're also going to get that point of -1, -1. Okay, so to put the graph in, this is looking a little scruffy, so let's try and put this graph in now. We know that we've got a turning point here. We've got that turning point. We've got the turning point here. We've got the turning point here. And it goes through a point of inflection. Now, I really should substitute in my value here into here, but if you've not got access to a calculator, that could be quite tricky. And we basically just want the sketch of this, the shape of this. So we know the point of inflection is somewhere here. I don't know where that's actually crossing. I suspect that it's kind of, I don't know actually. Right, so there's some sort of point of inflection here. Now we should really find that coordinate point of inflection as well. Yes, we actually do need the point of inflection. So you're going to need to substitute in this to find that point of inflection. And that means that really you need a calculator there as well. So if you've got a calculator, you could use your GDC anyway. And again, for sketches, we normally want to know where we're crossing the axis as well. So especially if we've got our GDC, just find out your roots of the polynomial as well. So you can do a polynomial root solver on your calculator too. Okay, so we're missing a couple of things here, and I'm not going to do them just for time-wise. We're missing this point of inflection here, this, and this point here as well. Let's look at what they do. Yeah, okay, so they've actually come up with the points of inflection, but they don't seem to care about where this crosses the x-axis in this case. Okay, but normally we do put on the x-axis intercepts. Okay, well, there you go. So there's another point here in the book which talks about if f has a point of inflection at x is equal to c and the gradient at that point is 0, then it's called a horizontal point of inflection. Now, we did this with x to the power of 3, and that's where we were saying that that has a horizontal point of inflection at y is equal to 0. Okay, so so that's just an extra condition. Not all points of inflection have a gradient of 0. That's an important point to know. Okay, now with example 30 and example 31, again, it's going to take ages for me to go through this, and I'll just talk through what they're doing, and talk through how to do something, but I'm not going to do each of these because they're quite repetitive. And they're coming up with these sign tables, they're getting lots of practice, and you need to get lots of practice too, but they're relatively repetitive. So let's have a look then at example 30. Let's just talk through the strategy for this one. Okay, it says find any turning points and points of inflection for this thing here and justify your answers. Well, obviously you're going to need to work out dy dx, and you can see here that you've got a combination of the product rule to use, but also the chain rule in one of the sides of the product rule there. So this is u and v, but for v, when you differentiate that, you'll also need to use the chain rule, although it's quite easy because the derivative of what's inside is actually just 1. Okay, so you're going to need to do that twice. So there's a lot of technical working out to do there. Okay, and so to get the second derivative, find any turning points. Well, turning points are obviously, again, when is our dy dx is equal to 0, and then consider your second derivative, okay, at those particular points in order to decide whether you've got maximum or minimum turning points. Okay, and then for points of inflection, again, you're going to need to set the second derivative equal to 0, and again, we need to check the concavity. Check concavity either side to make sure that we actually do have points of inflection, and we need to do that by maybe just checking a point slightly on one side and slightly on the other side of that point which we've chosen there, or of that supposed point of inflection. Okay, and justify your answers, and you can justify answers by creating sign tables if you want to. To be honest, I'd use no sign table for this one. Okay, just to find your turning points, and then for your points of inflection, again, you're going to set this equal to 0, and then just check either side of your supposed point of inflection. Now, this one is a bit of a head scratcher as to how to draw it. We definitely know that this is a positive quartic, so it's going to look something maybe like this, or remember it could look like this, or remember there's another option here. It could end up that, say for example, this point goes upwards, and you're getting something like this. Okay, so when you bring this upwards, you lose that extra turn. Now, again, as I say, this one's a bit of a head scratcher because actually you get two answers when you set the gradient is equal to 0 here. You'll end up getting this one, and you'll get one somewhere over here as well. And then you think, well, how do I draw that? Because normally I've got 3 turning points. I've got 3 places where I've got a gradient of 0. So 2 places harder to think about how to draw it. So that's why you need all of this technical information in order to help you draw this graph out. And once you've got your graph, I think it looks something like this, then when you find your points of inflection, again, normally you have 2 points of inflection. You've got 1, 2 there. Do that in colors, okay. on sort of your normal quartic. And here you'll find that you have that as well. You'll find that you have a point of inflection here as you go from this increasing gradient to a decreasing gradient. But then again, you'll flick to an increasing gradient on this side, at the other side of the point of inflection. So we'll have, again, 3 turns like normal, 1, 2, 3. Okay, 3 turns. That means 3 different sections for its concavity, and that means we've still got our 2 points of inflection in this case as well, as we would have in this model here. Okay, so having a look at this, they say, well, there we go, there's the graph, and they talk here about your point of inflection. They've labeled that as 3, 0, and that's actually a horizontal point of inflection as well, because the gradient there is equal to 0. But they haven't labeled here the other point of inflection. Now, again, think about this one. So where is the other point of inflection here? We've definitely got one. Where's the other one? Well, again, increasing gradient, decreasing gradient, increasing gradient, 3 turns. Somewhere in the middle of this turn and this turn, there's also this point of inflection. So we've got, there and there. So we've got somewhere around here by the looks of things. And in fact, if you have a look up through the working out, you can see they've also got the point of, if you have a look at this, here we go. So let's just take a little section of this. So you can see when they've got this, there's actually going to be 2 points there. X is equal to 3, but also X is equal to 1 is going to be a point of inflection as well. Okay, and I mean, it's worth working through because, these are quite technical. And there's this other little bit here as well, where they're just checking the change in the concavity either side of what they think is their point of inflection. Okay, remember you need to check points of inflection could actually be turning points. Again, like y equals x to the power 4. Okay, so last question here, and example 31. Again, I'm just going to talk through it a little bit. Example 31 here. Just find all the turning points and points of inflection. So same process again. Determine their nature and justify your answers. Again, same process again. Yeah, I'm going through that 100 times. It says find the intervals where the function is concave upwards. Same. Where is this true? And concave downwards is all of the, is the opposite of this. Sketch the function, including any maximum, minimum, and points of inflection. Well, it seems like we've done this already, but let's have a look, see if there's any issues in this one. No issues to start off with. The substituting x is 0 and x is minus 3 over 2 into f dash dash of x. So we definitely have a local minimum for the negative x value, but when we have 0, we have, it says it's inconclusive. It's inconclusive because we don't know. We may well have a point of inflection, but you know what we need to do? We need to check the concavity either side. Okay, when we check the concavity either side of 0, that you see that you have concave downwards and then concave upwards. And then that obviously means that we do have our point of inflection. It's not the same on both sides, otherwise we'd have a turning point. And then you can sketch the graph, and it's looking a bit similar to the last one, in fact. Okay, well, there you go. I'll stop there. This is exercise 4O. Lots of questions here. These look like short questions, but obviously there's actually a ton of work here. And it's important that you get lots of practice so that you get good at this. Okay. Well, thanks for listening in. And next time round, we are dealing with sketching the functions of the derivative when you're given the original function. Okay, so thanks for listening in. Hope to see you next time.